Thanks, Michelle. Can you see my screen okay?
Yes.
Okay, great. So thank you very much to the editors and reviewers of the paper, and particular thanks to Michelle for setting up this first Bayesian analysis webinar. It's an absolute pleasure to be presenting here. So I'm going to talk about our paper, a Bayesian Conjugate Gradient Method, and these are the people who are authors on the paper. There's myself, John Cockayne. I'm a postdoctoral researcher at the Alan Turing Institute. There's Chris Oates, who's a professor at Newcastle University and the Alan Turing Institute. Ilse Ibsen, who's a professor at North Carolina State University, and Mark Girolami, who's a professor at Cambridge University and at the Alan Turing Institute. So I want to start by unpacking the title of the talk. So the core phrase here is conjugate gradient method. And I'm sure many of you will have used the conjugate gradient method before. It's among the most widely used solvers for linear systems of equations. So equations of the form AX equals B, where A is usually for conjugate gradients a sparse matrix, and it's particularly often used when A is derived from the discretization of, for example, a partial differential equation. Now, the fundamental property of CG that's important for this talk is the fact that it's generally an approximate solver. So it doesn't usually, or it's not usually used in such a way that it will return an exact solution to the linear system, but rather the algorithm is terminated at such a point that the solution returned has a small amount of error. And that's where the Bayesian part of the title comes in, because what we're aiming to produce is a probabilistic numerical method. So this is a solver that's probabilistic in nature, a numerical method for solving the problem that's probabilistic in nature in the sense that it returns a probability distribution that's designed to quantify that error. And we're going to be trying to produce a probabilistic numerical method that has a Bayesian interpretation. So putting that all together, the talk is about a probabilistic numerical method for solving linear systems, and the probabilistic numerical method is going to be ideally Bayesian, and it's going to have a relationship to the conjugate gradient method, which we'll see how it's related throughout the talk. But before we get to the Bayesian conjugate gradient method, I wanted to give some background on how we solve linear systems in general from a classical perspective. So just to solidify notation, the problem that we're interested in solving is the problem of finding the vector x star, which is defined implicitly through this equation ax star equals b, where A here is assumed to be a d by d invertible matrix, and x star and b are each assumed to be d-dimensional vectors. B is assumed to be given, and x star is the unknown which we'd like to recover. At many points in the talk, A will be assumed to be symmetric and positive definite, particularly towards the start of the talk, but later in the talk, when we introduce the Bayesian conjugate gradient method, that requirement will be dropped. So this problem hardly needs motivation. It's one that most people who work in mathematical disciplines will have encountered at undergraduate level, and it's been studied for thousands of years, and I would say is the background of modern scientific computation. So most people who work in computational disciplines, and particularly people who work in the solution of PDEs, for example, or even people who work in computational statistics, will encounter this problem very, very regularly, either explicitly by calling solvers for linear systems that are related to their work, or implicitly through the software that they use solving linear systems internally. So there are, broadly speaking, two classes of solvers for linear systems. The first, which I would wager most people are more familiar with, are direct methods. And these aim to solve the linear system in some sense in one shot. So you pass in your matrix A and your vector B, and you get back a vector, which in exact arithmetic at least, is exactly the solution to the linear system. And a good example of a direct method, which I'm sure most people will have used before, is the Cholesky factorization. This is a direct method for solving linear systems in which the matrix A is symmetric and positive definite. And if you want to solve a linear system using a Cholesky factorization, you follow three steps. So first, you compute a Cholesky factor. This is a matrix L, which is lower triangular, and which has the property that A is LL transpose. And this animation on the right here is showing the access pattern of a Cholesky factorization algorithm as it executes. Then in step two, once we've found that factor, we need to solve so steps 2 and 3 involve solving two linear systems, LZ is B and L transpose X star is Z, where these systems are now very, very easy to solve because of the lower triangular nature of L. So this is just a passive forward substitution and then a passive backward substitution. So the Cholesky factorization is an incredibly powerful algorithm and is usually going to be the default if you've got a a linear system where A is symmetric and positive definite, but it's not universally the best method to use in such a setting. And one setting where an alternative might be preferable is when your matrix A is sparse. So the naive cost of Cholesky factorization is order d cubed in computation and order d squared in storage. And when the matrix A is sparse, that order d squared in storage doesn't go away. So even though you may require much less than order d squared elements in memory to store the matrix A, the Cholesky factor, when the Cholesky factorization is applied naively, is still going to usually be dense. And of course, there are direct methods that mitigate this and would produce, for example, a sparse Cholesky factor, but this is also a motivation for a different approach, which is to use an iterative method. So as the complement to direct methods, iterative methods, instead of producing a solution in some sense in one shot, aim to produce a sequence of iterates, these guys xm, which converge to the true solution to the system x star as the number of iterations goes to infinity. And crucially, each of those iterates is meaningful in the sense that it achieves a small error, or it achieves a bounded error in some norm as a function of n. So it's often possible, so the crux here is that it's often possible to elicit an iterative method that's faster than a direct method if we're prepared to accept a small error in the result. So perhaps the most widely used iterative method is the conjugate gradient method, although there are many other iterative methods which don't have any relationship to the conjugate gradient method or to Krylov space methods in general. This is, I would say, the workhorse of a computational solution of PDEs, particularly elliptic PDEs. So there are many, many different ways of deriving the conjugate gradient method, but the one that I'm going to present is based on the idea of minimizing this quadratic functional f of x. So this is a nonlinear functional, which it's straightforward to show has x star as its unique minimum. And you can show that by just taking the gradient and setting to 0. But if we ignored the relationship between f of x and this linear system, then a sensible way of finding the minimum, which is x star, the solution to the linear system, would be instead to perform gradient descent on the functional to find this minimum. So if you recall in gradient descent, we take steps in a sequence of directions, these guys sm tilde, and these directions are taken to be the negative gradient of the functional that we'd like to minimize. And this functional is sufficiently simple that we can compute that negative gradient very straightforwardly, and it's b minus a xm minus 1, where xm minus 1 is the point at which we're currently standing. And this guy is also known as the residual at the m minus 1th iteration. So the conjugate gradient method arises as a kind of modified gradient descent, and the modification that we make is to orthogonalize these search directions in a particular way. So we take the mth search direction from gradient descent, this guy rm minus 1, and we orthogonalize it against the previous search direction, and the inner product with respect to which we orthogonalize is the inner product induced by the matrix A, which defines the linear system. And it's straightforward to show that if we do this, and after we normalize these search directions by dividing them by their A norm, then we obtain a set of search directions that are orthonormal with respect to the inner product induced by A. So the inner product between Si and Sj is a Kronecker delta in the A inner product. So what I have here is an animation showing gradient descent versus the conjugate gradient method for solving a linear system, which I've just generated in 100 dimensions and then projected down into 2 dimensions. And these contours are the contours of this quadratic functional f of x. And what we see is that the conjugate gradient method very, very rapidly converges to the true solution, whereas gradient descent exhibits this kind of zigzagging going back on itself, which is prevented by the fact that we orthogonalize the search directions in CG. And another nice property of CG, which you can kind of see happening here, is that it provably approaches or reaches the true solution x star in d iterations, again, assuming exact arithmetic, whereas gradient descent may take many, many more iterations to even get close to the true solution x star. So this animation finishes at d as 100 iterations, and we can see that the gradient descent solution to the linear system is really still quite far away from the truth. So some other properties of the conjugate gradient method, which are important, particularly when we compare it to the Cholesky factorization approach to solving the linear system, is its computational cost. So we can show that the computational cost of CG is order md squared in computation because it requires 1 matrix vector multiplication per iteration. So if we can get away with doing much less than D iterations, then the algorithm will run much, much faster than the Cholesky factorization approach. And it's only ordered D in storage. So we don't need to store any additional matrices. We just need to store 2 or 3 additional vectors over the course of the execution. So this really is much, much lower cost in terms of memory than the Cholesky factorization. And there are some theoretical properties of the conjugate gradient method which are particularly important to the talk. And these revolve around the concept of a Krylov subspace. So the Krylov subspace of order M, generated by a matrix A and a vector B, is obtained by taking the span of B and the first m-1 powers of A applied to B. And it's straightforward to show, in fact, that these search directions, which we obtain by modifying the gradient descent search directions, actually form a basis of this Krylov subspace. And that allows us to prove an optimality property. So if I let Km star be this affine space, which is obtained by taking the Krylov subspace Km generated by A and R0 and shifting it by X0, then I can show that Xm is the optimal element in that Krylov subspace in the sense that it minimizes the error in the A norm, so the norm induced by the matrix that defines the linear system. And this allows us to also prove a rate of convergence for CG. So we have an upper bound on the relative error, again, in the A norm. We can show that it's bounded above by this term on the right here, where 2 things to note: that this is a geometric rate in M. M appears in the exponent here, so it's quite fast. And this rate is controlled by this number kappa of A, which is the condition number of A. So when A is symmetric and positive definite, as it's required to be for CG, this is given by the ratio of the largest and smallest eigenvalues of A. So if A is well conditioned, it's possible that because we have this geometric rate, we'll reach the solution fast, we'll attain a small error fast enough that we can terminate with much, much fewer than D iterations and have a much faster algorithm than some direct methods. So now I want to shift focus because this talk isn't only about the conjugate gradient method. What's important is that we're producing a probabilistic algorithm that is similar to the conjugate gradient method. And so I want to talk about what probabilistic numerical methods are briefly and why we might be interested in using them to solve linear systems. So as I've said, probabilistic numerical methods are a class of numerical methods that return probability measures designed to quantify numerical error. And in this figure on the right here, this is kind of a cartoon of a probabilistic numerical method for solving linear systems. So we've got this guy X star, which is the true solution to the linear system, obviously. And then we've got this Xm, which we can think of as an iterate from some underlying iterative method. So some classical iterative method like CG. So whereas that's a vector in the space that X star occupies for a classical numerical method, a probabilistic numerical method returns a distribution which is designed to express how confident we are that we've identified the truth. And these methods are called Bayesian if the output is a posterior distribution, which is somewhat of a simple definition, but it turns out to be quite complicated to define what a posterior distribution means in the setting that probabilistic numerical methods occupy. And if you're interested to learn more, this paper, which is appearing in Science Review later this year, goes into detail on that. So why might we be interested in using probabilistic numerical methods to solve linear systems? Well, the motivation that appears in this paper is in an application of probabilistic numerical methods as forward solvers for Bayesian inverse problems. So the conjugate gradient method isn't a silver bullet. It produces an iterate that converges very rapidly to the solution, but it's still very, very possible to have non-negligible error, perhaps because the dimension of the problem is just so large that we can't afford to expend an arbitrary amount of computational effort to solve the linear system, or perhaps because we've got a fixed computational budget that we can't possibly exceed, and that's not sufficient to drive the error down to a point where it could be considered as negligible. And in this setting, the probability model could be very useful, and the way in which we show it's useful in this paper, or think about it being useful in this paper, is in this application to Bayesian inverse problems. So typically, Bayesian inverse problems involve application of numerical methods to evaluate the likelihood. And where those numerical methods involve the solution of linear systems, what we can think of you doing is using Bayes CG to construct a new forward solver, a new likelihood, and therefore a new likelihood, which quantifies the discretization or truncation error in that forward solver from not having been able to expend enough computational effort to drive the error down to 0. So what we obtain then is inferences that are robust to discretization of the forward solver. And I've got a cartoon showing that here. So this blue line is, which I've labeled Oracle. This is the posterior distribution if we had Oracle access to the solution of some underlying linear system, which defines the forward problem. And then this red line here is what we would obtain if we just applied some method like CG, and we didn't drive the error down to a point where it was negligible and just used the solution that it returned anyway. And it's straightforward to show that doing this can lead to bias and overconfident inferences. So here I've got the posterior distribution peaked somewhere quite far away from where this Oracle posterior is peaked, and still very confident about the wrong answer. And we note also that it doesn't have much support near where the Oracle posterior distribution has support. So the idea is that if we use a probabilistic numerical method to solve the forward problem and incorporate the measure of uncertainty that we get from that method into our likelihood, then we can obtain a posterior distribution which is still biased, so it's still peaked somewhere far away from where the Oracle posterior distribution is peaked, but it's widened to account for the fact that the forward problem wasn't solved exactly, and that leads us to question how much we can trust the inferences represented by that peak, that map point. So that's the motivation for probabilistic numerical methods. And now I want to introduce the probabilistic numerical method, which we've presented in this paper, which we call Bayes-CG. So aspirationally, we want to produce a Bayesian probabilistic numerical method. So we need to specify a prior distribution and some information, which would form a kind of analog of a likelihood to produce a posterior. So we're looking to use conjugacy properties in order to construct that posterior. So we need a Gaussian prior, which is what we have here. So X is assumed to be a priori Gaussian with mean X0 and covariance sigma 0. And then we're going to use data provided by some set of search directions, which crucially are not assumed at the moment to be the same as the CG search directions. This is just some arbitrary set of linearly independent vectors in d dimensions. And we'll use them to produce the posterior. So if I put all of them into this matrix capital SM, then it's very straightforward undergraduate statistics to show that the posterior distribution has this form. So it's again Gaussian, thanks to those conjugacy properties of conditioning Gaussian distributions on linear information. The posterior mean looks like this, and the posterior covariance looks like this. And the specific form of those two distributions isn't particularly important, but what is important is to notice that to compute them, I need to invert this matrix lambda m. So that's slightly disappointing because I've taken one matrix inversion problem and I've just replaced it with a different one. This one is only m-dimensional, whereas the original inversion problem was d-dimensional, but it's still kind of disappointing to have to perform an inversion at all when it raises the question of why we didn't just invert the original matrix. But if we look at the form of this matrix lambda m, it's pretty clear that there's some structure here that we can exploit. And in particular, lambda m is the Gramian matrix formed by taking the inner product induced now by the matrix A sigma naught A transpose, and then computing the inner product of all the search directions with all the pairs of search directions with respect to A sigma naught A transpose. So the idea inspired by CG is that if we can produce a set of search directions that are orthonormal with respect to this matrix, then lambda m will just be an identity matrix, thanks to that orthonormality, and the posterior distribution will be simplified. We won't have to do any matrix inversion to compute it. And that's the first theoretical result that we provide. So if we let our search directions be defined like so, so the first search direction, S1 tilde, the unnormalized search direction, I should say, is just the initial residual. And then the nth search direction is defined in an identical way to how it's defined in CG, except for that instead of orthogonalizing using the A inner product, now we orthogonalize using the A sigma naught A transpose inner product. So it's straightforward to show that after we normalize these search directions, we obtain a set that's orthonormal with respect to the matrix A sigma naught A transpose. And that in turn simplifies the posterior distribution, as I've said, and in particular gives it this convenient iterative form. So I can compute xm by taking xm minus 1 and just adding on this vector multiplied by this scalar. And I can compute sigma m by taking sigma m minus 1 and then adding on the outer product of that vector with itself. Sorry, subtracting the outer product of that vector with itself. And even more, if I don't want to store this d by d matrix sigma m through the iteration of the algorithm, I can just store these vectors sigma naught A transpose Sm and then I can compute sigma m post hoc. So now let's look at the computational cost and in particular compare this to CG. So the cost in terms of CPU time is still order MD squared in computation, but that's just the computational order. And in fact, we need 2 to 3 matrix vector multiplications per iteration, depending on how the algorithm is implemented. Whereas in CG, you'll recall that we only required 1 matrix vector multiplication per iteration. So the cost is slightly higher. And in terms of the storage cost, now, whereas CG is only order D in storage because it only needs to store vectors, now we have a storage cost that's order MD, where M, of course, is the number of iterations performed. And this is due to the need from the previous slide to store these search directions, these sigma naught A transpose XM over the course of the algorithm to compute the posterior covariance. So the cost is slightly higher, particularly the storage cost could be quite a lot higher, but it comes with uncertainty quantification. And perhaps that's sufficient justification for accepting this slightly higher cost. So we also have some theoretical results which mirror the theoretical results that we saw earlier for the conjugate gradient method. The first theoretical result concerns an interpretation of the posterior mean as having optimality properties in a particular affine space related to a Krylov subspace. So now if I take the Krylov subspace Km, the nth order Krylov subspace generated by the matrix A sigma naught A transpose and the vector R naught, I rotate it by sigma naught A transpose and then I shift it by X0 and I let that be Km star. Then I can show that Xm, my posterior mean from Bayes CG, is the optimal element in that affine space Km star. And the sense in which it's optimal is that it minimizes the error in the norm now induced by the prior precision matrix, sigma naught inverse, rather than by the matrix A, which was the optimality result that we had for CG. But this gives us a nice property, which is a sense in which Bayes CG can be made to replicate CG, which is that we notice if we take sigma naught to be A inverse, then the sense in which the posterior mean is optimal coincides with the sense in which it's optimal in CG, because this term that pre-multiplies the Krylov subspace vanishes, as does the A sigma naught inside the Krylov subspace. And then the norm also coincides with the A norm, which is the sense in which CG's iterate is optimal. And furthermore, we can show that these search directions are the same if we take this choice. So I would emphasize that that's not a practical choice, because to compute the posterior covariance matrix, we would then need to invert the matrix A, which is the thing we were trying to avoid doing in the first place. But nevertheless, it's a nice mathematical property. And this optimality that we showed, that we've shown in this theoretical result presented on the previous slide, also leads us to a convergence rate for the iterate from Bayes CG, so the posterior mean from Bayes CG. So we can show that the relative error xm minus x star divided by x0 minus x star, now computed in the prior precision norm, is bounded above by this term on the right, which again is almost identical to the term, to the bound that we obtained from CG, except for that the condition number which controls the convergence rate is now the condition number of this matrix sigma naught A transpose A, rather than the condition number of A itself. But this gives us some inspiration for how we might accelerate the convergence of Bayes CG, because if we can choose sigma naught so that this condition number is close to 1, then, well, one would hope that this upper bound would mean that the posterior mean was going to converge very, very rapidly to the truth. So now I have some experimental results, and I'm going to focus in the talk on the simulation study that we performed in the paper. We also have an application to electrical impedance tomography in the paper, in which we show that by constructing a new likelihood for this tomography problem that depends on the posterior covariance from Bayes CG, we can obtain the desired robustness to discretization error in the inferences over the parameter from the EIT problem in the inverse problem, but I'm not going to present that here. It's presented in the paper. So as mentioned on the previous slide, the most sort of critical choice that we have to make is the choice of prior covariance, because firstly, one can show that this determines the posterior covariance because we don't have any noise in the data. Furthermore, because this affects so strongly the rate of convergence that we obtain in the posterior mean element from base CG. So I have three choices of prior covariance, which I'm presenting here. There are a couple of other ones, again, discussed in the paper. The first one is sigma naught is A inverse. So mathematically, we can show that this should produce an iterate posterior mean that replicates the iterate from CG. And we'll demonstrate that empirically in the experiments. Then we have a choice, sigma naught is I, which I've labeled here uninformative. It's uninformative in the sense that it doesn't give a preference to any particular direction in the solution space a priori, though of course it says things about how large the norm of the expected norm of the solution will be. And then the last choice, which is the one that we consider the most practical in the paper, is to use a prior that's based on a preconditioner. So a preconditioner for a linear system is a matrix P, which has two properties that are very important. The first one is that we can compute its inverse very straightforwardly, because the matrix has some structure that we can exploit to compute that inverse. And secondly, we have the property that if we take the condition number of P inverse applied to A, then this is much, much smaller than the condition number of A itself. So assuming that we can find such a preconditioner, and preconditioning for linear systems is a very, very widely studied thing. So often we will be able to find a preconditioner for a particular problem we're interested in. Then given the theoretical result that we had a few slides ago, it makes sense to set my prior covariance to be P transpose P inverse, where P is that preconditioner. And in the experiments that follow, I'll be using a generic preconditioner, which is derived from computing an incomplete Cholesky decomposition of the matrix A, which is assumed to be sparse, or which is sparse in the simulation study, with zero fill-in, which is more or less a Cholesky decomposition in which we enforce the sparsity pattern of A on the lower triangular Cholesky factor. So for the experiments, A will be taken to be a random sparse matrix, and this is drawn using the MATLAB function sp_randsim. The dimension is 100, and I'm going to draw many test problems X star from a unit Gaussian distribution in 100 dimensions. Then I'll apply Bayes CG to M is 100, so to convergence, and I'll compare this to two different sets of directions than the Bayes CG search directions, which are the CG search directions, just for reference, and also a set of just directions which are referred to as a priori optimal. So these are derived from an optimality argument that we present in the paper, but for the purposes of the talk, we can think of them as just being essentially random. So these are the results for the convergence of the posterior mean. So on the left here, I've got these two solutions to the linear system from iterative methods based on different search directions than the Bayes CG search directions. So for the CG search directions in the top left, the y-axis here shows the 2 norm of the error for the iterate, and the iteration number is on the x-axis. The bottom left, we've got these a priori optimal directions, which you think of as being essentially random. And then we've got solutions, posterior means from Bayes CG for these three different choices of prior. So what should we take from this? Well, CG exhibits this sort of this rate that we see here. The a priori optimal directions seem to converge extremely slowly. And in fact, if we were to plot this on a linear scale on the y-axis instead of a log scale, we'd see that the rate was essentially linear, because that acceleration that we get, that we've proven that the posterior mean has this geometric rate, only applies if we use this special set of search directions from Bayes CG. And in the case of these essentially random search directions, we don't get that benefit. If we use an identity matrix for the prior covariance, we see a rate that's not actually that much better than the rate that we get for these a priori optimal directions. And that's more or less because the prior is so uninformative that the condition number of the condition number that's controlling the convergence is just too large for convergence to be fast. But then when we use these more informative prior covariances, we see an acceleration. So when we have sigma naught is A inverse, modulo some numerical differences, some differences that are due to numerical implementations, which are discussed in the paper, the convergence rate is more or less identical to the convergence rate from CG. Whereas if we use this preconditioner prior, then we have a massively accelerated rate of convergence. Now, it should be emphasized that this is a little bit misleading because we're not comparing like with like. Of course, we could use the preconditioner that we've computed to compute the prior covariance, within CG to accelerate convergence there as well. And then we would see a rate of convergence that was even faster than the rate that we get from Bayes CG. But nevertheless, it's nice to know that there is a practical choice of prior covariance for which we obtain a fast rate of convergence in the posterior mean. But that's not the whole story. What we're really interested in here is not just how rapidly the posterior mean converges, but also how useful the posterior covariance is. So how useful that whole description of the uncertainty in the solution of the linear system can be. So to assess this, we make an ansatz that the posterior distribution is well calibrated if the true solution to the linear system looks like a draw from the posterior. So this is kind of a slightly fluffy statement at the moment. And the way we're going to assess this, practically speaking, is by drawing a set of test problems from some distribution. In the slides that follow, it will just be a unit Gaussian distribution. And then we'll assess whether those random X stars, those random linear systems solutions, look like draws from the posterior by evaluating this statistic, which I call the Z statistic here. So Z of X star is the norm of X star minus Xm squared, and it's the norm with respect to the matrix sigma m dagger. So the sigma m dagger is the Moore-Penrose pseudo-inverse of the posterior covariance. And it's important that we use a Moore-Penrose pseudo-inverse there because the posterior covariance is typically singular. So obviously we can't use a standard inverse. But using the Moore-Penrose pseudo-inverse is fine because we're only interested in assessing the uncertainty quantification in the range of sigma m. And in its null space, we've identified the true solution exactly. So we don't need to care about what the uncertainty looks like in that null space. So if we accept this ansatz that the posterior distribution is well calibrated, if X star looks like a draw from the posterior, then we can show that this guy Z of X star ought to have a chi-squared distribution with d minus m degrees of freedom. So this procedure of producing a set of random test problems and then evaluating the test statistic Z of X star is precisely what's shown on this slide. We've run Bayes CG to 10 iterations here. So the reference distribution that we expect our test statistic to follow, if the ansatz is true, is given by this dashed gray line here. So this is the chi-squared distribution with d minus m, which is 90 in this case, degrees of freedom. The other lines represent solutions from Bayes CG and also a solution provided by these a priori optimal directions. So what we see here is that the only test statistic or the only posterior distribution from which the test statistic matches its theoretical distribution is the a priori optimal directions, which are essentially random. And in all the other cases, we find that what we have is a conservative posterior distribution. That conservativeness is shown by this left shift towards the origin. And that conservativeness seems to be exacerbated by having a more informative prior covariance. So when sigma naught is I, we have only a moderate left shift. And when sigma naught is A inverse, this is what's shown right on the left of this graph here, which is zoomed into in the right panel. When sigma naught is A inverse, it's quite conservative. And when sigma naught is P transpose P inverse, it's very conservative. And what's the issue here? Well, the issue is that heuristically speaking, if we were to try and write down a likelihood for the inference problem that we conduct when we solve the forward problem, when we produce the posterior distribution for Bayes CG, we would see that the search directions here are a function of X star. So on the left-hand side, this is the relationship that we're trying to enforce that Sm transpose of X star AX is equal to Sm transpose of X star A X star. But of course, the left-hand side here ought not to depend on X star, it ought only to depend on X. So, and if we were to take these search directions to be the Bayes CG search directions generated by X instead of by X star, then we would have a likelihood that had a forward map that wasn't linear in X star anymore or in X. So this conditioning, this conjugacy property that we've exploited to construct our posterior distribution is not strictly correct in the setting when we use the Bayes CG search directions because they depend on the solution to the linear system X star. So we have various approaches to address this described in the paper. And these are things that we're still working on as further developments of Bayes CG, various ways to empirically correct for this poor UQ, perhaps by introducing some sort of ad hoc scaling factor on the posterior distribution, which is one of the approaches that we explore very briefly in the appendices of the paper, and which we're taking a more concerted effort to follow now, as well as by constructing more informative priors, such as, again, the Krylov prior, which we discussed briefly in the paper, which are informed by the Krylov subspace, which we expect the solution to occupy. And then other work that we're undertaking is work studying more basic iterative methods, such as Jacobi iteration and Richardson iteration, to try and understand their properties and whether we can fix this, this nonlinearity that occurs in the search directions in a more rigorous and structural way. So thank you very much for listening. I hope the presentation has been informative, and I'd like to say a particular thank you again to the editors and the reviewers of the paper, as well as to everybody who submitted a discussion, particularly the people who submitted invited discussions, Xudong Li, Ethan Fang, and Philip Hennig, and everybody who submitted contributed discussions as well. Thank you.
Thank you, John, for the informative presentation. So as you mentioned, there have been two invited discussions by Philip Hennig and Ethan Fang and one of his students. We have here Ethan Fang, so I will give him the screen to outline his discussion.
Sure. Yeah, thank you very much. So now I want to add, can you see the slides well?
Yes.
Okay, let me go to the full screen. Okay, so first, let me and my collaborator congratulate the authors on this wonderful paper for the following novel contributions. First, so by the way, so I work on some optimization, but I never worked it from a Bayesian perspective. So in optimization, usually we just give an error bound for the solution, but usually the bound is loose. I think this paper provides a novel approach to quantify the solution uncertainty and also quantify the solution's quantity by giving a posterior distribution. So, so the authors also provide a novel approach like a hierarchical prior to address the scaling issue. And the authors provide efficient implementation and also an interesting application to a very interesting field. So in our discussion, we provide a different perspective to explain the Bayesian conjugate gradient. So in particular, we consider this following system here, so which is equivalent, but in a different formulation. So in particular here, this sigma now is the same as the sigma now in the Bayesian CG paper. And taking this part as an M matrix and this part, yeah, sorry.
Ethan,
yeah.
I'm not sure if it is the same for everybody, but we haven't, we are not seeing your next slides.
Really? Oh, okay,
yes.
let me, so
okay.
Does it work now?
Yes, now it's working, perfect.
Okay, okay, maybe I cannot go to the full screen. So yeah, so we provide a different formulation for the, different but equivalent formulation to the problem by the authors, AX equals B, solving for X. And what we have here is that by giving a different formulation and solving this problem, which is M, X tilde equals B, and just applying the applying the classical conjugate gradient method to this problem, mx tilde equals B, by solving for x tilde, which has shown to be equivalent to the Bayesian conjugate gradient. This reformulation should help the authors to simplify several proofs, like to derive the convergence of the Bayesian conjugate gradient and also the convergence rate. So, here, let me go to the next slide. So, and there are some interesting follow-up questions I think worth investigating. I'm interested in these questions. Like, so first is like doing the Bayesian inference here. So what's the mixing time here? Because we assume that after in the first few iterations, the solution might be far from the optimal, from the optimal solution. But how many after how many iterations the inference would become meaningful? And so because the conjugate gradient method has other like a counterparts for other optimization problem, like a proximal gradient method. So can the same method like Bayesian method generalized to other optimization method like proximal gradient method, which is also very important in solving many optimization problems, or like other method like ADMM or gradient descent simply. So I think this also motivates us to consider the algorithm-based statistical inference. Like just we do estimation, we have an estimator. If we can just provide like a posterior of the solution to the iterative method, that would be very interesting. Yeah, that's all I have. Yeah. Hello?
Yes, sorry, it took me some time to unmute myself. Okay, perfect. So is there a rejoinder from John or Chris?
I want to thank you, of course, for your response. It was really interesting to see that the proofs that we'd obtained could be obtained from the classical results for CG by just following this left and right preconditioning algorithm. And I must say, I wish we'd spotted that while you're writing the paper, because it would have simplified our job dramatically. And in terms of the discussion that you've provided, particularly the generalization to optimization methods is something that we've discussed amongst ourselves as well, and something that we're intending to visit in the future.
Great.
Perhaps I can also add my my thanks both to Ethan for the very interesting discussion of the paper, and also to Michelle and Bayesian Analysis in general for providing this forum to have this discussion. I think it's a great initiative, and I hope that that it goes from strength to strength in the months to come. Just on the specific point of Bayesian perspectives on other optimization methods, I think that's a very interesting question. Bayesian optimization is obviously a well-studied method in and of itself, but for example, if we think of integer linear programs or discrete optimization, for example, I have no idea how to approach those from a Bayesian perspective. I think it'd be very interesting to do that, in particular because if you think of an integer linear program, for example, the uncertainty in a sense is quantified by a dual bound. So you know how far away you are from optimal, but you don't really have a sort of a continuous expression for uncertainty, you just have a bound. So there's a lot of potential for Bayesian methods, and if someone has a bright idea for how to make this work, it would be tremendously exciting.
Yes, like you said, for the integer programming, I think in my experience, it's usually the case. By iterative method, you get the optimal solution very fast, but you don't know you get the optimal solution because it's actually upper bound converges to the optimal very fast, but the lower bound it takes like weeks to converge to certify that the solution is optimal. Yeah, I think if a Bayesian method could be proposed for integer programming, that would be extremely interesting. Yeah, but I think that is somehow fundamentally different from the conjugate gradient because it's not gradient-based method. Yeah.
Perfect. I would probably now open up the floor for discussion from any of the attendees. I believe that you can, anybody can unmute themselves, or the other possibility is to ask a question either in the chat or in the Q&A boxes at the bottom of the Zoom platform or the Zoom video. So please feel free to intervene and ask any questions. I will start probably with one question, which is motivated from the discussion by Philip Hennig. And I would like maybe to ask if it is possible. So Philip Hennig in his discussion makes a distinction between passive and active probabilistic linear solvers. Could you probably try to expand on that and clarify a bit the difference between the two?
Yeah. So as I recall, Philip defined a passive probabilistic linear solver to be one which tracks the standard solution from some classical method such as CG and just attempts to provide probabilistic uncertainty quantification for that method. whereas an active solver tries to use the probability model that's being built over the course of the iteration to improve the rate of convergence from the classical method. So the important thing to note here is that all of the probabilistic linear solvers that have been presented in this work by Bayes CG, and also in Philip's work on an approach to solving linear systems based on placing a prior on the matrix and learning about its inverse, all classify as passive linear solvers. And he believes that the sort of future of probabilistic linear solvers is in finding these active solvers that use the probability model to improve on the convergence rate. Now, I agree that using the probability model could give us avenues to do this. The challenge, I think, is, or rather, one of the interesting parts of this is that if we were to find an active probabilistic linear solver that fit into this model of producing a posterior distribution in the solution space, then that would naturally provide a set of preconditioners that we could use when working with CG. Because we have this interpretation that the prior covariance forms a preconditioner, or when computed with preconditioners, accelerates convergence. So equally, if we found a prior covariance which accelerated convergence in a probabilistic setting, then we could use that to construct a preconditioner for a classical numerical method. Yeah, I think this is an extremely interesting proposal, and it could have benefits for both probabilistic solvers and for classical solvers as a result.
Maybe I can just add on to the end of that. One of the great opportunities with active methods is that when you're working on a large computational code that involves many different numerical subroutines, such as integration, optimization, solving a PDE, the traditional approach would be to work out the computational complexity associated with each of those relative to the error incurred, and to balance those costs in such a way that you're optimally using your computational budget. But that requires a numerical analyst, and if the computational code is large or complicated, then a numerical analyst might struggle to optimally balance the computational resources across those subproblems. But in the active context of probabilistic numerics, these numerical agents that you've developed to solve these tasks will be able to report some belief about how accurately they solve those tasks. Those beliefs can be aggregated into a single probabilistic distribution that's amenable to something like an ANOVA. So in ANOVA, we can look at the output of the complicated code and say, well, how much of the variation here is being, or how much of the uncertainty here is being driven by this particular numerical subroutine or this numerical subroutine? And we could optimize the computational budget in a sort of active or intelligent way based on the statistical representation of the numerical uncertainty. I think that's a very exciting possibility in the context of active probabilistic numerical methods.
Perfect, thank you.